Hello, everybody. So we're going to start chapter 12, and this whole chapter is about structure determination. So what you're going to learn here are two different types of spectroscopy methods that will help you either confirm the identity of a certain structure, or given an unknown, you could figure out the structure. So this is just the first part. And I'm going to focus on mass spectroscopy today. In the next segment, we'll talk about infrared spectroscopy. So we'll talk about the mass spec, just basically how the instrument works. The main thing you'll be doing is interpreting mass spectrum data, and then I'll look at some functional groups that are common, and you can see very common fragmentation patterns from those. Okay, so as an organic chemist, and even when I was a graduate student, I was using mass spec a lot. And the reason is a lot of times you're running reactions and you're synthesizing compounds that either have been made before and you can confirm that you made the correct thing, or you've never made it before, or it's never even been made at all by anyone, and you need to confirm that what you actually made is what you think you made. So it's an instrument, you inject your sample, and it can spit out information about the mass of a molecule and fragments of that molecule. So it basically determines the molecular weight. And I'm going to show you just basically how the spectrometer works. First, there are three components. You have an ionizing source. This is a source of electrons to help kick out an electron from the molecule that will make that molecule charged. Then there's a mass analyzer. The reason why we need that is you're going to get some fragments and you need to just sort through them and get the masses of those. And then there's a detector that's going to tell you that mass and help separate the ions observed and count them. You can basically get a quantity of those fragments. So first of all, you have your organic molecule. We're just going to say a generic RH. A small amount of that sample will then be injected into your mass spec, and it'll undergo vaporization and ionization to form what's called a cation radical. So we're going to basically bombard it with electrons, and what comes out of this is a cation radical. The reason why is you would actually kicked out a valence electron to produce a radical, unpaired electron, and then you lost an electron, so it has a plus charge because it's a cation. Okay, during this energy transfer, this can actually fragment the molecule. And some molecules are more robust than others, but generally the main organic molecule is not high in abundance intact, and what you normally see are a lot of fragments of that molecule. Let's take a look at the actual instrument. Here is the area where we inject our sample. It goes through a separation here through a magnet. There's a detector here, and that spits out a spectrum on the computer. So first of all, we inject the sample. You could do this with a needle. A lot of times you're working with a large number of samples you want to analyze. So sometimes you can have an array of vials, and then there's a robotic arm that'll inject and go through that whole array of samples. Once it enters into the mass spec, basically there's this ionizing electron beam. This electron beam is going to dislodge an electron, a valence electron from your organic molecule. That's going to create your cation radical. But this is high energy, so that molecule can fragment. And the fragments that are also cation radicals will go through a slit here and proceed in this bent portion here. This is this curved pipe here, be exposed to a magnetic field. And basically those fragments will be separated out, shown here, and a detector will be able to tell you the mass to charge ratio. So for our purposes, our charge is a plus charge. So basically, overall, what you get out of this is the mass of that ion. These positive fragments, they're sorted through this detector, and then you get out a spectrum that'll display those peaks. Here's an example of a mass spectrum that you'll analyze. Basically, you have this M over Z, which for you guys, what you want to think about is this is the mass of the actual parent molecule, unfragmented, and then some smaller fragmented ones. What's on the y-axis is basically how much abundance there is. So this is a relative percent abundance. And if you just take a step back and look at the spectrum, you'll notice one main thing. There's a main peak. We call this the base peak at 100% intensity. So basically this is relative abundance. So it says most of the fragments observed are this base peak. That doesn't mean it's the parent. The unfragmented radical cation is the parent, which is just the whole molecule. We call that M+. So the reason why these are charged is that's what the mass spec is doing. It's analyzing those fragments that are charged. So this, in this case, would have been the parent with a mass of 44, and then it lost a certain amount of mass of fragment to give, so it lost about 15, which is classic for a methyl group, to give this main base peak. Okay, sometimes you see a smaller peak on the sides. Isotopes can explain this because remember, the mass of an atom of a molecule is a weighted average of all the isotopes that exist. So carbon, you have C12 is the main one, over 99%, but still there's some C13, C14 as well that will add mass to it overall. So what you can be seeing are the different isotopes. And this will come into play later. This will help us later when we're actually looking at identifying whether or not there are halogens. Okay, let's further look at this. So basically, we get the molecular weight from the mass of the molecular ion, but there are some compounds that are just too fragile and they don't exhibit or show the full intact parent molecular ion. So here you see you have 100% this base peak, but I don't see any other peak with a higher mass. So I'm missing that parent. So we'd have to use a more gentle method, and there's some softer ionization methods that can be used. Okay, one of the main features of mass spec is that you can kind of start recognizing certain pieces that can help you construct in an image of the structure of a molecule. So mass spec can provide somewhat of a fingerprint of a compound, meaning the molecule breaks down into characteristic fragments. So for example, if you look at this neopentane here, one way that this can fragment that's obvious is to just have a methyl group break off. So what you would get is the cation portion being the tert-butyl fragment and the methyl radical here. So the tert-butyl fragment and butyl fragments are a mass of 57. So just knowing certain fragmentation patterns, certain masses can really help you figure out what type of overall molecule you have. The other thing I want to note is that the positive charge here after this fragment, this is a cation radical. When it fragments, you could get a cation and a radical. The positive charge will remain with the fragment that best stabilizes it. That's typically what's going to happen. So tert-butyl, because of the hyperconjugation, can better stabilize this cation. Okay, let's analyze an actual molecule. And so we're going to look at hexane. So I already know it's hexane. I'm not looking at a spectrum and trying to figure out an unknown. So I'm going to use the information I have for hexane. The formula is C6H14. If we add up the masses, 12 for carbon, 1 for hydrogen, we get a total of 86 for that parent, intact, unfragmented hexane. So here's our spectrum of hexane. Do I see an 86? I do, right here. See a little sideband here for isotopes, but there's my parent peak right there. M+ is 86. What else do I see? There are actually peaks at 71 here, which was small, still a fragment, 57, 43, and 29. So 57, that's the base peak. Most of your fragments that go through the detector are registering as this fragment 57. Let's analyze why we observe this fragmentation. So hexane has 6 carbons in a chain. This is normal hexane. After we generate the cation radical, we have M plus 86. M over Z, or your mass, is 86. How do I get these other masses? This is what you need to think about. What can happen to this? I've already shown you, you could clip off a methyl. So minus a methyl, that's 15 mass units. 86 minus 15 is 71. That can explain this guy. That's not a prominent peak though. Our base peak is 57, shown here. What happens here? Going from 86 to 57, you lost 29 mass units. That corresponds to an ethyl. That makes sense. You could fragment here, get an ethyl, and this butyl. Sorry, yeah, so fragmenting ethyl gives you this guy, butyl. Okay, what else? Another prominent peak is the 43. You could have fragmented straight in the center to give your propyls. So half of 86 is 43. And just further analysis, you keep going, you get the ethyl that we've already talked about of 29. Okay, so this is kind of the method of how you analyze a spectrum and explain the peaks. That's one thing that you may be asked to do, just explain why we see the certain peaks. I'm going to now just go through a couple common functional groups and the types of peaks that you do expect. So with hexane, it was just a hydrocarbon. So we just fragmented along the CC bond. But different functional groups will give different types of fragmentation. When you have alcohols, you do what's called an alpha cleavage, and you can have a dehydration. So for an alcohol, the alpha carbon is the one it's directly attached to. So an alpha cleavage is just clipping it right next to it. So you could clip it here, and what you get left is this group as your cation portion. So this is good because this can also be stabilized by resonance, shown here. So if you see an alcohol, just know you could clip off one of the groups attached. And there may be different groups that you can. You can clip off a variety of different alpha substituents. Okay, the other thing you could do is a dehydration and remove water. You guys have actually done this in our alkene section to prepare alkenes. You can dehydrate this with acid and heat, and you get water, which will be neutral, and your cation radical will then be your alkene. So you would look for that. So if you have an alcohol, you would look for these two. Okay, amines, very similar, will also undergo alpha cleavage. Clipping it off here gives this cation, which can be stabilized as the imine, shown here, stabilized by resonance. Halides are really interesting because if you recall, halides also have an isotopic pattern, and depending on what you're looking at, the pattern may be different. So I'm going to focus on two, chlorine and bromine. The chlorine, a chlorine-containing molecule has a specific isotopic pattern because of the Cl35 and 37 isotopes. These exist, so you have an M, if you have a chlorine, of just your overall mass based on 35, and then another one, M plus 2. 35 plus 2 is 37. So these represent the two chlorine-containing molecules of different isotopes. And the percent abundance of those is going to show up as roughly 2 to 1 in a spectrum. So if we look at this, this is chloroethane. We can see M here and an M plus 2 shown here. So it's about 2 to 1, maybe not exactly, but still right here, I would recognize that, oh, I might have a chlorine-containing molecule. Then you can look for a mass minus 35 to see if you have a fragment that's minus 35 or minus chlorine. The bromine containing compounds also have a pattern due to bromine 79 and 81. And these are in roughly 50-50%, so roughly 1-to-1 ratio. An M and M plus 2 is what you'll see. So let me go through two specific examples. 2-chloropropane. I would expect this 2-to-1, M and M plus 2. So right there, if you're given a spectrum where you see the parent and you see this isotopic pattern, start thinking, oh, this might have a chlorine in it. Then look for the next obvious thing. A chlorine is going to be 35. So if you have your main out of the two parent isotopes, the main 178 minus 35 minus the chlorine will be 43. So you do see this as a significant base peak. You also see something else here, minus 15, which hopefully now you're recognizing is methyl. So you note that as well. Let's look at an example with 1-bromopropane. Look at this parent. I said bromine has a 1-to-1 isotopic pattern. So if you see this 1-to-1 in the parent, start thinking that it might have bromine in it. Look for minus 79, which indicates the loss of 1 bromine. Here, this would be your base peak. Okay. Carbonyl compounds have specific fragmentation, and one of them is involving a rearrangement, the McLafferty rearrangement. So basically, you can have a carbonyl compound, and if you have enough carbons along a chain to have a hydrogen here, you can undergo a rearrangement where the O forms a bond with this H, and you form an alkene here, and this fragments to give you this alkene fragmentation product and this enol. So again, carbonyl compounds, if you have a hydrogen here, so you can fragment here, and what you would observe is this fragmentation with a hydrogen added. The other thing carbonyl compounds can do is undergo just your classic alpha cleavage right next to the carbon of that carbonyl. This is going to form this cation, which can be stabilized by resonance, a lone pair here stabilizing that plus charge on the carbon. Okay, just the final bit for this section is just to work through an example. So what we're going to do is just figure out what compound we're looking at, and then figure out what the mass of the parent ion is and several fragments. So this, I'm going to walk you through this. This has 1, 2, 3, 4, 5 as its parent chain, 5 carbons, and then it has a methyl off of it and an OH off of it. So pause this, write a formula, figure out the parent ion and its mass, and then based on what you learned about alcohols, what sort of fragmentation or other product could you get out of this after you put it through a mass spec, and then try to figure out those masses. So pause this, work on this problem, and I'll go over it. Okay, so here's our solution. This is 2-methyl-2-pentanol, and you can have 2 main fragmentations resulting from a dehydration, removing water, and alpha cleavage. And your alpha cleavage you can do involving 2 different groups. So first of all, this is your parent, M plus is 102. You have your 5-carbon chain and then a methyl and an OH off the second carbon. A dehydration removes water. So you can remove an OH and an H here to give this more substituted alkene. Removing water, minus 18, gives a mass of 84, plus your water. So that's one peak that you would expect to observe. So the molecular ion, not the base peak though, it's the parent but in smaller amount, and then you would see 84. There are 2 others you'll also see because of the alpha cleavage. So alpha cleavage just cleave next to the carbon attached to the OH. So you could cleave and remove this propyl group, or you could cleave and remove a methyl group. So if we remove the methyl group and you'll end up with it, your OH still. This is just showing the more stabilized resonance form, but basically you get your 87. So minus 15 for a methyl group, you get 87 as one of the fragmentation peaks. The other thing you can clip off and undergo is the propyl group in your alpha cleavage and give the M over Z equals 59. Okay, this is where I'm going to end. And then next time we're going to talk about IR, infrared spectroscopy, which will help a little bit more with your analysis with your lab work. I know you guys are doing that with the labs in the last section of elimination and Diels-Alder. So it all helps solidify that. All right, I will talk to you guys soon.